Hi everyone, so today I'm going to present our work entitled the compact triband patch antenna design at terahertz frequency. So I am Youssef Amraoui. I am a PhD student at LISAC Laboratory at Sidi Mohammed bin Abdullah University, Fez, Morocco. So our work, so we began our work by introduction, followed by the presentation of the antenna design method, then the results and discussion, and finally conclusion. So the first important question to answer is what are terahertz waves? To answer this question, Figure 1 presents the position of terahertz band in the electromagnetic spectrum. Generally, the terahertz band is situated between the millimeter wave and infrared bands within the frequency range of 100 GHz to 10 THz. This corresponds to a wavelength range between 30 micrometer and 3 millimeter. Now, why terahertz waves? It's necessary to understand the different properties of terahertz waves. So one of the primary advantages is transparency or penetration. Terahertz waves can penetrate certain non-conductive material such as plastic, paper, and even some biological materials. Unlike X-rays and gamma rays, terahertz waves are now ion no are now ionizing, meaning they pose no health risks. It is safe. Another property is the high-speed communications. Such traceways offer the advantage of high-speed communication, and we have the resolution. Tracewaves have high resolution due to the smaller wavelength than microwave. So the principal disadvantages are cost. So generally the costs associated in the development of traceways are expensive. The second disadvantages are the proposed losses and atmospheric absorption that increases in this frequency. So for that, it is important to develop a high gain antenna. So our objectives here are to develop a compact, simple, and multi-band antenna for terahertz frequencies. So let's begin with the proposed antenna design. So a tiny multi-band resonance antenna operating within the terahertz spectrum has presented a multifaceted challenge leading research to explore variety of methods to achieve this capability. So this work suggests a triband microstrip antenna designed for today's application with an overall substrate area of 1 multiplied by 1.5 millimeter square as depicted in figure 2. The antenna's radiating components are printed on top of polyimide substrate with a lossless tangent of 0.008 and a relative permittivity of 3.5. Various rectangular and semicircular slots varying in length L but with the same width W and same radius R are printed in the radiating element patch as shown in figure 2a. Utilizing the finite element method based on this high frequency structure simulator HFSS, the design and simulation processes were carried out with a central field of width WF and length LF. The antenna is stimulated in this configuration by a microstrip transmission line technique. The antenna's bottom view is observed in figure 2b. The conduction patch is the primary component of a microstrip antenna that change return losses. Surface current distribution, bandwidth, impedance matching, and radiation patching to modify antenna performance. In the current research, the radiating patch's performance was enhanced through the implementation of a slotting technique. This study uniqueness is attained through the implementation of patch modifications aimed at enhancing the current distributions on the antenna's surface. The equations available in the literature simplify the calculation of radiating element dimensions, as shown in equation 1, 2, 3, and 4. The detailed dimensions of the antenna elements are indicated in Table 1. This study used a parametric-centric technique, systematically varying one parameter at a time while maintaining the others intact, to identify the ideal antenna size and performance. In Figure 3, the return losses S11 in the lower, middle, and higher frequency band may be varied by varying the values of W4, L4, and W3. Figure 3a exhibits the effects of changing the value of W4 from 0.05 to 0.15 mm. It can be noticed that the increasing value of W4 shifts the resonance frequencies from 123 to 120.8 GHz and 169 to 167 GHz and 184 to 180.5 GHz in the lower, center, and high frequency bands, with a rise in S11. Figure 3b also showed that the lower bands shifted from 124 to 123 when the value of the L4 increased from 0.1 to 0.3 mm, while the middle band remained almost unchanged. The highest band decreased from 185 to 182 GHz with an increase in return losses S11 in the lower and middle bands as shown in Figure 3b. Changing the value of W3 from 0.15 mm to 0.07 results in the upper frequency band shifting from 179 to 181 GHz, while the middle band still unchangeable, and the lower band shifts from 123 to 121 GHz with an increase of S11 as presented in Figure 3c. Thus, the suggested antenna's best dimensions are W4 equals 0.1 mm, L4 equals 0.3 mm, and W3 equal to 0.1 mm. So the recommended antenna design procedure is shown in this section. The suggested antenna starts with a rectangular patch as displayed in figure 4, antenna 1, with a minus 10 decibel bandwidth of 5.6 GHz. But in this instance, the antenna is operating only at single frequency as appear in figure 3. Then to shift the frequency towards the multiband, different rectangular slots are introduced onto the patch of initial rectangular patch as depicted in figure 4, antenna 2, and antenna 3. Additionally, a simulation of the standing wave ratio SWR will be employed to describe and evaluate the suggest the suggested antenna, since the SWR value controls how well the antenna adapts. If the SWR value is less than 2 decibel, the antenna will be perfectly adapted. As presented in figure 5a, the recommended antenna has a SWR of 1.7 1.07 decibel, 1.06 decibel, and 1.2 decibel at the lower, middle, and higher frequency bands, respectively. And figure 5b displays a graph depicting the efficiency value at the resonating frequencies. So at a frequency of 123 GHz, the efficiency is approximately equal to 81%. At 168 GHz, the efficiency reaches 86.06%, and finally at the frequency of 182 GHz, the efficiency peaks at 91%. A maximum gain of 4.34 decibel at 168 GHz and 5.66 decibel at 182 GHz and 3.97 decibel at 123 GHz is what the simulation results show for the recommended antenna as shown in figure 6. Now the surface current distribution over the radiation patch is apparent in figure 7 to help explain the multiband behavior of the recommended antenna employing different slots in the patch. In figure 7a, b, and c, the resonating frequencies exhibit the highest current density within the transmission line and semicircular section. Table 2 offers a comparative analysis between the recommended antenna and other antennas documented in the existing literature. When considering the comparison table, it becomes evident that the suggested technique outperforms existing method documented in the literature. This advantage is especially notable when it comes to applying the technique to design a multiband antenna, where other approaches may pose challenges or complexities. Finally, compared to the other antennas, the suggested antenna performs far better. Now, conclusion. So in the present research, a triband antenna with various slots in the radiating elements patch is employed for terahertz applications. Thus, this antenna can serve as an effective solution for surveillance, radar, medical imaging, and radio astronomy applications. In order to further improve data transmission capacity and system reliability in this frequency ranges, this research also sets the path for future improvements in integrating MIMO system. And thank you.